The velocity triangle of Francis turbine. This is a very important topic for understanding the design of Francis turbine. So before construction of velocity triangle, let us understand some important velocity terms which are used for velocity triangles. So these are the inlet condition. This is outlet condition for the Francis turbine velocity triangle. So inlet relative velocity is u2, inlet relative velocity is v2, inlet absolute velocity is c2, inlet whirl velocity is cw2, inlet axial velocity is ca2, inlet blade angle with respect to radial is beta 2, inlet absolute velocity angle with respect to radial is theta 2. Now outlet condition, outlet mean bucket velocity or blade velocity is u3. Outlet mean relative velocity is v3. Actually it should be blade, not bucket. And outlet mean absolute velocity is c3. Outlet mean whirl velocity is cw3. Outlet mean axial velocity is ca3. Outlet mean blade angle with respect to axial is beta 3. Outlet mean absolute velocity angle with respect to axial is theta 3. So all the velocity are in meter per second and unit of blade angle is in degree. So these are the rotor or runner of the Francis turbine. So in Francis turbine, the flow fluid is radial at inlet and axial is outlet. So you can see the flow in a radial at inlet and this is axial outlet. And if you look at the blade shape, if you look at the blade on top view at inlet, you can see the blade is like this, where the flow of fluid is in the radial direction. And if you look at the side view at the blade at outlet, angle is profiled like this and blade is outlet axially for the Francis turbine. So you will use this uh, pictures for construction of velocity triangle for easy understanding. So these are the inlet absolute velocity CW2. Draw the inlet absolute velocity in the direction of inlet guide vane, that is IGV angle, and IGV angle is shown as a theta 2 with respect to radial direction for reference. So you have to draw the C2 from the IGV angle theta 2, and inlet absolute velocity depends on the water head. Higher the head, inlet absolute velocity will be higher. Now the inlet runner T velocity U2. Draw the inlet runner velocity in the same direction as the direction of runner blade T velocity, and it depends on the speed and diameter of the runner, and it is expressed as U2 is equal to pi d2 n upon 16 to 1000, where d2 is a runner blade inlet diameter in millimeter and is a runner blade speed in rpm. So with this you can draw U2. Now the inlet relative velocity, inlet relative velocity V2, we have to join the starting point of C2 and a starting point of U2. This will give you V2, that is the inlet relative velocity. Now the inlet whirl velocity, that is CW2, that is a whirl velocity. So tangential component of inlet absolute velocity is called the inlet whirl velocity, that is this one, CW2, and inlet mean this should be not whirl, this should be axial velocity, that is CA2. The axial component of inlet absolute velocity is called inlet axial velocity. So these are the inlet axial velocity, that is CA2, and beta 2 is the blade angle with respect to radial, which is shown here, beta 2. Outlet mean relative velocity, that is V3. So draw the outlet mean relative velocity in the same direction as the outlet blade angle, that is beta 3, which is shown as a V3. This is V3, and this V3 will be larger than V2 because of some reaction occurs in the blade. So now draw the outlet runner blade tip mean tip velocity in the same direction as the direction of blade tip velocity, and it again depends on the speed and diameter of runner blade outlet mean diameter. So U3 is equal to pi d3 into n upon 60. D3 is a runner blade outlet mean diameter in millimeter and is RPM. So through which we can calculate U3. Then inlet mean absolute velocity, that is a C3. You have to join the starting point of V3 and end point of U3. This will give the inlet outlet mean absolute velocity, that is C3. The outlet mean whirl velocity, outlet again transition component of outlet mean absolute velocity is called outlet mean whirl velocity. So CW3 can be positive or negative. If this side it is positive, if it is this side is negative. This side is positive in the same direction as the direction of the blade, and this is opposite direction. But the best design will be CW3 should be minimum. Then outlet mean axial velocity CA3. So axial component of absolute velocity is called outlet mean axial velocity, that is CA3, which is shown here. And theta 3 is outlet mean absolute velocity angle, that is theta 3. So this is how the inlet and outlet velocity triangle is drawn. So I hope you have enjoyed this. Thank you for watching.